So welcome everyone. I am Partha Pandey from School of Electrical Engineering and Computer Science, and I am going to introduce today's speaker, Professor Xian-He Shan. This is the fourth talk of the series of pilot talks we are doing as part of the PA Processing in Memory Technology Workshop, NSF sponsored workshop. So Professor Shan is the director of the Scale-Up Computing Software Laboratory at the Illinois Institute of Technology. He is a distinguished professor and the Ron Hospung Endo Chair of Computer Science. He was a department chair from 2009 to 2014. He is an IEEE Fellow and Golden Core member of the Computer Society. His current research interests include parallel and distributed processing, memory and I/O systems, software systems for big data applications, and performance evaluation and optimizations. With this, please join me welcoming Professor Shan, and Xian-He is all you now. Please go ahead.
Thank you, Partha. Thank you, everybody. I think somehow always somebody I come here. This is need me admit into this meeting. Do I need to do that, or some of you can do that? Or?
I am doing that. We are doing. The organizers are doing. Please don't worry.
Okay. Thank you, everybody. I know people still join in. Thank you, everybody, to join this. Thank you for the committee, workshop committee, to invite me to give this opportunity for this presentation. So my talk is on the challenge and the opportunities of processing in memory, and of course, our performance point of view. So the first part, of course, the challenge and the opportunity is the topic is really required by the workshop, right? They want to talk about this. But why a performance point of view? So this talk, I think, is complementary of last talk of this workshop, right? In the last talk, Stephen talked about this challenge and opportunities from industry point of view. So today I talk from a different view, from a performance point of view. So why performance? Because I'm high performance guy, right? I always working on high performance computing, so performance optimization. So that is my view from there. So we do not talk about this particularly power consumption, so other securities. We really focus on performance. So that is the topic, and we will talk today. And then from here, so we start when we say performance. What is the performance, right? So the performance, we start with a computing performance. HPC is the computing performance, and from there we'll say, okay, all the computing performance is really because the memory access delay, and then will become a memory system performance. But how to solve this memory system performance? We have this solving this memory war problems. We have to go back, to have this computing in memory. So that's how motivate, how to integrate the PIM into this whole big picture of this memory systems and also this architecture of high performance systems, ecosystems. So we want to say the PIM is very important because the current hard topic is, the intelligent computing, AI, and the deep learning. But everybody knows the deep learning, the idea was, proposed and introduced more than 20 years ago. So why that become so popular during the last 5 or 6 years? So because now we have a big data and we have high performance computing. But high performance computing at this stage is for computing. HPC cannot handle big data very well. So we have this memory war problems. And from there, how do we solve this memory war problems? PIM is a part of the solution. So that's why, this is the whole flow of this talk. of this talk. So we start with memory war problems. And the memory war problems, I think many people know that. Even last, most of you know that. Even last talk, Stephen mentioned this, gave a very similar picture. So today I want to talk about the timeline of this memory war problems. We started with 1990. We first mentioned the memory is the performance bottleneck. This is called the memory bound speed up. That is a part of my dissertation. So that's why I want to start there. In 1994, we got this memory war problem first really formally introduced by Bill Wolf. Bill Wolf was the president of National Academy of Science at that time. And then another timeline is 2004. 2004, the community adopted multicore. And then, of course, there's another timeline. It's 2012. 2012 is the time we got the National Initiative for Big Data. So we follow these four timelines to talk about our research, the changing, and at the end we say how, how this PIM fit into the whole big picture. How do we use that also into this big picture? So we said we started with 1990. This is memory bounded speed up. Memory bound, of course, this started from Amdahl's law. Amdahl's law say, so you cannot really utilize parallel processing because, in here, if you use parallel processing and in fact, you only can parallelize this much, 90% and 10% will quickly become you cannot improve, right? That is become your something you cannot improve. But the 90% is how many processors you can use. You probably can use 18 processors or 16 processors, that much. You cannot be scalable. So then in 1988, that is 20 years later, John Gustafson introduced, say no. So in fact, when you get more power, you get more work to do. So this is called a fixed time speed up. So how much work you can done in the you can do in the fixed time, that is you scale up. So you could get a linear speed up. But then in 1990, immediately I said, no, this is not what you can do. It's really limited by your memory. But not only limited by your memory, we introduce this memory function, right? This is very important. In fact, this involves your algorithms. This you have a reuse rate. How to utilize your memory is really related with the remote rate. So your memory, between your memory and your computing, there's a function. So this function depends on your trade-off. This basically say your memory is your bound, but how you solve your memory bound, you need to consider not only consider your scheduling problems or system support, you also have those thinking about your algorithms, right? So later they have analysis discipline in the completed analysis that's called memory bound. This is the memory bound function. But in 1994, based on memory bound, you should get a big memory, right? If the memory bound, you just big memory. But of course, you only have limited transistors in memory on chip. So in the later in the 94, as we mentioned, Bill Wolf introduced the memory war problem. They don't know, if you get a big memory, the memory is the bottleneck because the gap, the performance gap between memory and your CPU become larger and larger, right? So how do you solve that? The traditional way to solve that is memory hierarchy. But when you get the memory hierarchy, even on single processor based on your memory functions, you could have these curves. So your memory always have a memory bound. That means you always have bound on your fast memory. And recently, this is a before this is a based on we published more than 25 years ago. But more recently, Berkeley developed this called roof sealing. They really you can measure the bound. So the bound have two bound. One is your theoretical bound, one is your practical bound. So if your practical bound really below your theoretical bound, that means you could have improved, right? You can change your system support or your programming skills. You can improve. But if that already close to a theoretical bound, then you don't have much to improve. So that is how that from the theoretical result go to this really roof sealing is now you quite used a lot in this HPC community. So that it take about 20 years to from from the theoretical result become generally accept. So that is the memory wall relation between memory wall and the memory bound. But another we come back now, say that okay, now we should go to another two timeline. It is multi-core technology. Another is big data initiative. What is the influence on the multi-core on us? Certainly, this is something worth to study, right? This is one Amdahl's law is 40 years in the 40 years anniversary. This Mark Hill, he read a paper. They said, what is Amdahl's law for the multi-core? Of course, they said you use some translators, certain number of translators, you can make a cell for it's R. Use R translators, you can make a cell. Then you can make that heterogeneous, or you can make that heterogeneous. Heterogeneous is you could have a one single one, very powerful to do the sequential part, and homogeneous one is everybody the same, right? So basically, say based on Amdahl's law, based on Amdahl's law, the multi-core also not scalable in the term of cores, because even you can put more cores in there. So if you do not improve your or increase your problem size, you will go down. Heterogeneous is better. He called unsynchronized and unsymmetric. You could go to 256, and then this one basically you see it's about the Amdahl's law. You will probably go to 16. You cannot do much, and in here you probably can get into 64. It's the best is 64. So it's not scalable. But then of course I followed up. I said, oh, okay, based on your same assumption, it's multi-core scalable for scalable computing. So if we increase the problem size, it's multi-core scalable. And in fact, yes, it is scalable. But in practice, it's still not scalable, right? Even we get a perfect parallel, we have no sequential part, perfect parallel. There's still multi-core, still not scalable. So what is the issue? So then we started this, we go back to the memory, say, okay, we assume this perfect parallel, there's no sequential, only the cost is data access time, WC is data access time. Based on this, we want to see if that's scalable or not, if the multi-core scalable or not, based on their number of cores. So we get this results. If this WC is the access time, we get this. This is a linear. Right? It look like it's linear, but assumption this have to be a constant. So that means the WP is constant when you give a number of p's. But the question does WC is a constant number or not? So let's go back to this conclusion. Now we come to conclusion. So multi-core is scalable, but under the assumption I have to admit somebody in. But under the assumption, data X time is fixed and doesn't increase with the amount of work and the number of cores. But that's difficult to achieve, right? Basically, if you are shared LF3, you have a 3 or shared memory or last level cache, then you get more cores, then you get more data go to your shared memory, then you get more or shared cache, then you get more contention. Even if you have individuals, so if you want to coordinate, they all increase, the cost always increase with the number of um, cores. So that is, in fact, it's very difficult to attend. So these are technical issues. You have to solve the data access time. The scalability is your data access time. It's not your sequential part anymore, right? So that is, data access could be through remote or could be local, but even the local, you have the multi-core contention for your last level cache, you still have more cost when you get more number of processors. So that is the conclusion. So no matter what, you for sequential processing, you for multi-core, or if you are parallel processing, or you study scalability, no matter what, the bottleneck is data access. Multi-core cannot solve the data access problems. In fact, you add more pressure on the data access. So then the question is, how do we solve the data access delay? How do we solve that? Okay, my computer is slow a little bit. So what is the solution? The solution is the traditional solution is the memory hierarchy, right? Everybody know the memory hierarchy, but memory hierarchy has been there for 30 years. But what is the new change of the memory hierarchy? The new change, recent change for the memory hierarchy, you can what we call deep memory hierarchy or deep memory and storage hierarchy. So you get more levels, you get L1, L2, L3, or even L4, then you get the main memory, you get the persistent memory, and so on. If you consider parallel file systems, you get flash, the HDD, and so on. But not only for this, one thing is very important is we not only have a deep memory hierarchy, we not only have need locality, but also have a lot of concurrency, like out of order execution, speculatives, run ahead execution, and so on. And the other side, on your left side is multi-issues, multi-thread, multi-cores. So this new multi-cache, all this kind of thing. Like multi-issues, you can issue at one cycle, you can issue multiple data access instructions. And in the multi-threading, you think the multi-threading for parallel processing, but the multi-threading maybe not, right? It's maybe just try to solve your data access delay. So you get one cache miss or a page miss. So you instead you're waiting for the data come, you can pump up another instruction to continue execution, right? This is called out of order execution. So the next execution, if you get cache miss, you can get another out of order execution. So currently you could have 40 or 50 of this out of order execution. So how do we utilize this data access concurrency? So we think there's a lot of potential there. We really haven't, we studied the locality pretty well, but we haven't really solved this, utilized this concurrency. There's a lot of concurrency just available in the last 10 years. So we haven't utilized this hardware concurrency very well. This is one thing we published. We think is we'll talk about that more. Called some SIMAT modeling. But in addition to this deep memory storage hierarchy, we also have other solutions. This application specific integrated circuit is from there. You get GPU, DSP, AI chips, and you get many accelerators, right? The accelerator is good for certain applications, so we use that as, we only call that accelerators because it's only good for certain applications. So that mostly for data-intensive applications. Like we said, you can get this, this accelerator. Assume it's more like you can get the milk from the can very quick. But when you finish this, how do you get from data from outside? That's still a bottleneck. So you assume you can use for a while, but mostly, this accelerator only we call that accelerator. They can, if that is a computation intensive or you have a good locality, you can use that. But in general case, we still have the bottleneck behind that. We have a gap between the CPU and this accelerator to move the data. So that is, for data-intensive applications, it's still not good enough. So that now we get into the PIM. So now we get to the PIM. Say that, okay, accelerator is not good for certain applications. So we need for other applications. Can we reduce data movement? We can have a processors in memory, right? But we said that you process in memory, you have to with the same ransom of this memory. So that means you have to be slow. You cannot be very fast. If you're really fast, much faster than memory, then you still need a memory hierarchy, right? So then basically say you could have a small stool and maybe just specialize. If you're close to the milk, you can process the milk, and if if you're close to to meat, you cook for the meat. And so this is, for me, this is more like data movement reducer. You get less powerful in computing, but you reduce your data movement. So this is, when you use that, you have to put into this whole picture, of this data access and computing. So then say that how we get this PIM into this picture, then how do we really use PIM efficiently? So this is the same, really very similar with how to use CPUs, GPU efficiently, but this is in the memory. So in the memory hierarchy, become much more complicated. So then we have to study the memory hierarchy, right? So the memory hierarchy, can you really, the PIM contribute into this reduced movement, really can contribute into this total performance? So how much you can contribute, what time we can use it? This is what we want to study. So then we have to go back this formula. This is textbook formula, right? What is your CPU time? This is the final result, CPU time. You see your execution time and your memory store time. Memory store time is time CPU waiting for data. So from the data movement point of view, or we should reduce this. We should reduce memory store time. So how to reduce memory store time? If we optimize the memory performance, memory system performance, the goal is to reduce memory store time. It's the final goal for memory system optimization. So how do we measure this? How do we optimize this? As I mentioned before, this textbook solution is AMAT, average memory access time. If you do not remember the term, but so all this counts is your hit time. If not hit, you have a miss, and then you have a miss, you have miss penalty, and then the miss and the miss penalties. The miss is get this measured by miss ratio, and the miss penalty is the average miss penalty, right? But then we mentioned now we have a concurrent data access. What is the concurrent? How do we get the concurrent data access factor in there? So we introduce this CMAT, concurrent AMAT, concurrent AMAT. Then you have another method called APC. The APC is you can measure SIMAT very easily, very efficiently. So it's 1 over SIMAT. Okay, now we say how we use this, right? So this is the classical formula or textbook formula. Say what is memory store time? Memory store time is really the average memory access delay or memory access time. Then you times what's the ratio of data instruction, and then in fact into SIMAT is the same thing. You really the ratio times the SIMAT. And the SIMAT already consider overlapping, so you minus out the overlapping. You minus out the overlapping. Then we will see what we introduce a little bit more about SIMAT. Since we use that, right? So the SIMAT is for me it's very beautiful one, very beautiful one. So AMAT is very beautiful. Everybody use that because AMAT you have this analysis tool. You get what you hit, or if you not hit, you can miss, and you miss, you can miss penalty. And also the miss penalty, you can recursive. What is L1's miss penalty? L1's miss penalty is L2's hit, and L2's miss, then L2's miss penalty. So you can recursive again and again. And SIMAT is extension of AMAT to consider concurrency. So the SIMAT also recursive. So this formula, I think, very, very beautiful, right? So this is the miss ratio. Miss ratio the same as AMAT. And then what is the K1? The K is here. It's an overlapping ratio. And overlapping ratio, what is overlapping ratio? Overlapping ratio is the pure miss cycles over miss cycles. So then what is the pure miss cycles? And the pure miss cycles, it's a miss cycles without a hit. So that is a new concept. If you haven't heard that, I introduce a little bit more. So when you have miss, you said before, you said you get a miss, you have miss penalty. But now we say, okay, you get a miss, you may not have miss penalty because you may have, because you have multiple data access, you may have another one that get a hit. And your miss cycle may be covered by the hit cycle. So it's only one time the miss really hurt you, it's no hit cover you. So you get this is called pure miss. Every access, even you get 10 access, all get miss. Then that's called pure miss cycle, pure miss cycle. So very beautiful here is that this is recursive. This everything is recursive. You can have a K2, you got the miss ratio 2, and the miss ratio 2 the same as before, right? So here tell us what? Here tell us before we think of concurrent access or concurrency is here, you get a concurrent hit, you increase your bandwidth. But now we say your concurrent hit is not that important because your penalty really big. So it's very important that you reduce the miss ratio, then you overlapping. If you cannot reduce the miss, you try to cover that with the overlapping with your hit. And then this overlapping ratio is as important as your miss ratio. This I think in the old architecture community, even the OS community, when you do the scheduling, we really haven't done that. Everybody just working on this part, but now you have thinking the hardware changed, and now we get so much concurrency in there, we can overlapping that. So this is we go in there. We said we have 4 different cycles in current modern architecture. You got 4 different cycles. So you get a hit access cycle of hit memory access. You get a hit access cycle of a miss memory access. You get a non-pure miss access cycle of a miss memory access. You get a pure miss access cycle of a miss memory access. So basically, you really care is the right one. All the others is not that bad. You could get a hit, you could get a miss, but if you miss is covered by other hit, you still have a really good performance. You do not have that much penalty. So the really penalty is the pure miss, and you really want to try to reduce pure miss. you want to increase your data access concurrency. So here is the analysis. This we did on a real application. We can measure that. You can see before we only have the miss ratio, but now we have another thing we can scheduling over to management for the optimization. So you get the hit ratio, you get this concurrency overlapping. So in fact, with the SIMite, this is 0.6, and in fact, without this concurrency, if you do not count this, this is 3 times. This 3 times larger. So the concurrency is very important in here if we do that right, and this is by real measurement. So this is a real example. Okay, so that is our new metric. Say that okay, with the SIMite, now we have something new. We can have some new tools, another totally new dimension to optimize, or to reduce the memory stool time. But still, the question is how do you reduce that? How do you optimize data access time? So we got this idea called layered performance matching. With this SIMite. So what is the layered performance matching? They said, okay, you have a CPU, you have memory. The memory is so slow, right? Because we have memory war problems. So then you add into the memory hierarchy. When you have the memory hierarchy, we try to match the supply with the, match the request with supply. And in the beginning, we cannot because memory is so slow. But now with this hierarchy, we try to, each level, we try to match that. And by the end, the whole systems, you match this, the CPU requires, the data requires with the memory supply. So that is the idea. So what are the each levels requires and supply? The requires, of course, is your how much the generation on the L1 level is the generation of your memory request instruction, right? Then the L1's SIMite is inverse the APC, so you get this. This is the SIMite is the APC, the SIMite inverse APC, the supply rate. So you want to match this rate. With this matching, what the advantage with this matching? The advantage, we transfer a complex global optimization problem into simple local matching problems. So we simplify these problems into local matching. And with local matching, we can use concurrency, we can locality to improve that. The power of SIMite is include both locality and concurrency. You can get a good balance for this. So now that this is not only idea, we have algorithms to do that. We have algorithms to do that. These algorithms can tell you, based on this 4 cycles analysis, we can tell you how much, based on how much, you can tolerate of this memory stool time. We can tell you at each level, so what match, the match ratio, what is the match ratio you should achieve. So we have this whole analysis. We have the algorithms, we improve that. We prove that in about 1.5 years ago, but we just published one paper here, gave the totally theoretical results for the analysis, so we can develop a simulator about that, a totally new simulator. So currently, I only talk about one code. Look at the formula is only a simple one, right? Just tell you the concept. But in fact, this could be multi-core. And we also have multi-core version for this. We have the multi-processor versions. And also this memory hierarchy, you do not really need using all these memory hierarchies. Some of the technologies can be merged or into one layer. So we can get a term called tiers. So you have different technologies, their performance different, but they made on the same level of the memory hierarchy. Yeah. So this has become, you could concurrent access, you can jumping around. So this is a general, you have a general match. This you have a general match. So we will now talk about that. The concept the same, but just formula a little bit difficult to understand. Is you have to read the paper to understand the formula. So then we get this, you get this idea of matching. You get this, you can even get the formula, the algorithms to throw, or the methodologies, say how to do the matching. Can you really match that? And in fact, we do prove that. In fact, we can match that. This is engineering issues. But practically, maybe you have difficulties, but that is engineering issues. But theoretically, if you have enough concurrency, you have enough locality, you can. And now we say, you get this global optimization, really complete global optimization into local matching problems. So in fact, you can, right? You can focus on your engineering solutions. In fact, it's much easier to solve than before. Okay, so that is the end for the memory part. Now I have to, this is the PIM workshop. We have to go back to the PIM things. So how the PIM into this picture? PIM into the picture is very simple. After we understand the memory things, we can get PIM in here. So basically, PIM put another computing in here, right? And this computing, we assume there's no memory store time. So then, but the question is here, this computing is slower than this computing. So when you add the PIM, you need to think about, the overall, the CPU should be reduced. That means you have to reduce the memory store time enough to trade off. In fact, your PIM is slower than the general multi-core CPU. So that is the here is the trade-off, the decide. You have to decide what time you use PIM. You have to, based on this formula, you said, okay, when we use PIM, I can reduce memory store time so much. So even I slow down the computing a little bit, that's okay. So that's how that decide. So okay, now we can say that the PIM into the big picture. We get the two class of computing device, powerful CPU and less powerful PIM. And then this global picture is we call the sluice gate is this total picture. Have to decide what time you use that. But this again, our talking is about simple things, right? But in general, you have fan in, fan out. You get a branch. You get this remote memory access. You get not only one PIM, you get multiple PIMs. But we already see the basic formula, basic idea. So this we can in here we can go to all the details, but we can tell you all the ideas can apply for general case. But when you use that, you have to be very careful how to use this general concept. Just like you use the symmetry on the multi-core, you have to understand, you really understand what this formula means. You can know how to apply that. But in general, yes, you can apply. You can apply for general case. So now we get this, say, the data flow movement on the one movement. So what time you want to move data? What time you do not want to move data? So we just simplify this. We call it the DataflowV. This is how you decide what time you want to move data, what time you do not move data. So how you match that. And it's not just matching data access. Now you really have to decide where to do the computing. And as we mentioned, the computing is not that one PIM. You could have a different PIM. So you could also have a processing in storage, right? So this is a general solution. But today we're talking about the PIM. So we back to PIM. We go a little bit more emphasis on PIM. So how do you use that? Okay, your idea is good. Tell me how to use that. So you basically, when you into the big picture, people already done that, right? People say this is offloading. The only this already people already done that called offloading, right? What time you want CPU do that? What time we want PIM do that? So this when you use PIM, this is the first decision you have to make. The only thing is people based on people based on the traditional experience, they based on the myth. This based on the myth, right? So this is the pan. Based on last level myth. Based on last level myth, they say okay, if you miss high, this is a locality traditional locality method. If you miss high, should be this is should be in the PIM, because if you miss, of course, you miss high, your penalty is high. Your penalty is high, you should be in the PIM. So that makes sense. That makes sense. So then we said, okay, this is the first thing we want to compare. Okay, we want to compare. You talk about the myth. What about I talk about the pure myth? We said the pure myth is more accurate than myth. So then if I follow you the same thing, but I use a pure myth, see how we can improve this. How we can improve this. This is our first implementation. But the pure myth, say that it's a pure myth. It's a really pure myth. It's measured by the pure myth cycles, right? You get a pure myth. That means this myth have a pure myth cycles. So some pure myths have a more pure myth cycles. Some have less, right? Depending on how you're overlapping that. So we use this. We really use the pure myth cycles as this measure for which one is more important. So if your pure myth cycles is high, we say, okay, this is really damage us. It's not myth, but the pure myth is really hurt us. So we use this as the factor to decide which part of your loop to go to the PIM. So here you can see, this first loop, you only have a two pure myth cycle. And this one, the third one, you have a 6. So certainly by a pure myth cycle, so this one should be go to PIM, and this should go to PIM. So not based on myth, and based on myth, this pretty you get a lot of myth. You get a lot of myth, but this one had more pure myth. So they say this is more important. So this one go to PIM. So that is different. The only difference with the pure myth and myth direct comparison. Now you can see that our decision, we just use pure myth based on our pure myth. This you improve this by almost 20%. And also we move less code. We do only do half less offloading and get 20% better performance. And the same thing here, you compare this to another current better technology for offloading PIM. So this called graph PIM for the graph. So we get for the graph PIM, we get 11% better, and we get 1/3 of the fewer offloading. So you can see with this, but this CMAT is a measure of our matching. It's not perfectly used the matching yet, right? It's just, but it's easier to compare that. The CMAT is much better than AMAT, than myth. The pure myth is much more accurate than myth. It's a good comparison with the current method, but this is not with the matching. So can we directly use matching? So if your L3 is not match, it's not match, then not this matching the cost this part is the gap is big. The matching gap is big. I should put in a P. This is in the beginning we said that, right? If the gap you get down the match and the gap is big, you should put on the P. So we use this one. We use this, this gap. If you 60%. That means you get your weighting is 60%. Your total execution time, you get 60%. Only 40% you are doing computing. 60% you are waiting. So that the memory store time is too high. You done matching that. So then you need to move to P. So you can see this is even better, right? As we mentioned, this matching is easier to measure than your pure miss or miss. And in fact, this measure is easier and you get a better performance. You get a better performance. So the better performance is LPM even better than our co-PIM based on our CMAT, based on our CMAT. So the matching concept can be used, it's really simple and also can be used to decide the offloading. In fact, also, as we mentioned, you can put the PIM into the global picture, right? This into the global picture. So now we come back to this, we finish the PIM part implementation, but now we come back to say, how this PIM fit into this global picture of the data access. So PIM is still assumed data is already in memory. So the data either generated by computing or stored in the storage, right? So the PIM, the memory in general, what we talk about the memory is not persistent. So in fact, you need the storage is a large level of memory hierarchy. You still have, how to get the data from storage to go to memory. So in fact, we have implement this or use this with what we call a DataflowV on storage. So we can say we move this whole everything is deep memory storage hierarchy. The last level is the storage, and the storage is where the data is, right? And also implement this storage IO. It can be implemented by software. So it's easier for us to implement that. So in fact, this project we have supported by NSF is we have done 2 years now. We should get this we're working with the HDF group. HDF group is the group for the HPC IO. So we're working with them together to have engineers and postdocs and students working on that. We're supposed to, we should get our first release this year. So this we totally implement this matching ideas, multi-tiers. So you can get concurrent access. You can get this. You can get this jump the layers of the memory layers. So the whole implementation is quite complicated, right? You can put your data everywhere, anywhere, right, on the memory hierarchy or on the layers. But then, how do you manage that? How do you retrieve that? How do you manage that efficiently? So you get the independent management of each tiers. You have, complete data placement and replacement. So this is something we implement. So we have the software, so the user do not need to worry about that. We have this whole behind. Why we use HDF groups software, because in there you have a high-level language. You can give them, describe what you need for your IO, right? So with that information, we can provide much better support. So we do have this software under development, and I think the first release should be this year. Now, what is the take-home message? So what are the challenges of PIM from performance point of view? And the difficulty is PIM is, for me, is an accelerator, it's a data access accelerator for the memory war problems, or you can think of the memory move reducer to solve the memory war problems. So when you use that, you need integrate that and integrate that into the global solution of this memory war problems. So you have to into that consideration into the complex memory system performance, and this include storage as well. Then what are the opportunities? So therefore, many new applications, they are data intensive and even data driven, right? So we do need to solve this memory war problems. We do have something, you can processing. They get a simple computing, but get a lot of data. So the PIM has, you have this application. You need PIM, and also we have this integrated model. We call that DataflowV to develop the where PIM is pivoting factors. So PIM, one PIM can be contributed in the global performance. So this model can tell you. Of course, you could use the old method, based on myths. You can, but with the global picture, you can do that much better, right? You can do that better. And in fact, this new model will also consider the concurrency, data access concurrency. So we can do much better job, much better job. And of course, they have a lot of opportunities how to integrate with IOs, integrate with CPUs. PIM is not alone. You need to integrate this part of the solution. So how to do that? Of course, you get a theoretical methodologies, you get a practice experience, and in general, PIM itself is a part of the merging of computing and memory. And they are also a merging of memory and storage because the data pressure. So they have a lot of things need to do. In fact, from not only hardware, have hardware design, of course, is the main part, and then you have also have a language of systems, and you also how to feed this, the PIM into the global architecture. So therefore, many things, many things needs to do. Many things need to do. So here's a conclusion. So PIM should be utilized with the consideration of memory systems and multicore on CPUs. And opportunity is plenty as well as challenges. So the potential is high. In any case, the potential is high. So there are too many things need to do. So as you do more, you'll see there's more things need to do from language, from compiler, from OS, and from for me, it's the IPC systems, and from general architecture, circuit design. There's so many things need to do. Okay, that is the end of my presentation. I'm open for questions.
Thank you, Professor Xian, for your talk. So we already have one question in the chat, and folks can add questions on the chat or raise your hand. So do you see the question in the chat, or do you want me to read out? Question from Xian-He.
I can stop sharing. I can see that.
Yeah.
Let me stop sharing. Maybe I need an explanation. Would IC and the CPI of execution and PIM? What that mean? I don't understand the question. Overlaps as well as overlaps as well as.
So Xian-He, if you are on the audience, can you speak up, please?
CPI, I think CPI is, a cycle per instruction is a ratio, right? It does the same thing. This is come from the computing time, right? So this overlapping apply to everything about the instruction count. Is not overlap. This kind of count is instruction count. It's from your algorithms or from your architecture. But for the overlapping, we talk about it's more for the data access. For the data access, they change. I think you get a better overlapping. You get a better ratio of your CPI. So that's if I understand the question correctly. Also,
Professor Sun, this is Jan. I think I typed the question while I was on your slide number 25.
Okay.
You had formula between CPU time of the main CPU and the PIM. That's where it came from.
Yeah.
That was the first question. The second question was more insight on the design time, how we can sort of optimize or improve the architecture first before we, apply it to the runtime application. I hope that helps.
Yeah.
Yeah.
So for now, into the 25, I know this IC. For the IC, of course, we cannot change the IC, right? But you can separate the IC from your CPU IC, go to your PIM's IC. This is how you're offloading. For your CPI, this CPI, if you for CPI execution, now I know what you mean. CPI execution, this part is your computing part. We'll only talk about this, try to reduce the memory store time from the memory system part. Of course, we haven't touched the CPU design or this or the PIM CPI design or PIM's design. But your question is a very good question. In fact, this is we think a lot about this. The hardware currently, the hardware architecture, microarchitecture design, they really support the locality. All this, their concurrency is support the locality. So if you get a good locality, your concurrency will be effective. If you not good locality, you're not put into on the same row or same columns, so you miss, right? So they put a locality first, but now you get this random access. You do not have locality anyway. So how do you utilize this concurrency in there? So that's a big question. Current architecture design hasn't supported this very well. They're still based on locality. So that's why we say the CMIS is very powerful. It's very beautiful. Should be used by this microarchitecture people to think about that. How do you utilize this concurrency and locality together? Not always put the locality first. So that is a big question. So that's why we say that there's so many things need to do. Too many things need to do. Many of this is very fundamental. This is a really good question. Have I answered your question, Jie?
Yeah.
Thank you so much.
Is there any other question from the audience?
So I think this as I mentioned in the beginning, I'm an HPC guy. I just go to a performance analysis and go to a lower and lower into architecture. It's not I like to go to the architecture. It's because so I have to collaborate. I hire my postdoc from architecture field to do the work because there's a gap. There's a gap between this performance, modeling, and architectural practice. There's a gap. So there's a lot of things. I think when we use simulator, we found out a lot of simulator we cannot use. Even the GM5 is very popular in the architecture community, but if we use that, we miss a lot of concurrency because they designed for the memory, they designed for AMAT, so they can jump something, make that faster. And from under the old model, it's pretty good, but when you consider this memory access concurrency, so you miss something. So there's a lot of things from fundamental we have to do. Yeah.
So I don't see any question in the chat. Iran, do you want to say something to close the session?
I just want to say thank you so much for everybody to join us. Yeah, and thank you for the Professor Sun to give this exciting talk. So we already recorded this video, and we will tailor the video and also get the PowerPoint and put on the video and the PowerPoint on our webpage. So if for the people who are not be able to attend this talk, they should be able to find those information online.
Okay, thank you. Thank you all for attending.
Thank you. Thank you.
Thank you.
Thank you. Bye. Bye-bye.
Bye.